All right, let's go ahead and finish this problem. So we're trying to find the derivative of x to the fifth as a function. We're using the limit definition, which is pretty much always the same. And yes, there are variations of this, but if I had to remember one of them, this is the way I would choose to remember it, that the derivative of a function is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. And now we're just substituting in the actual function. So instead of writing f of x plus h, well, since my function is f of x equals x to the fifth, my f of x plus h is going to be x plus h to the fifth. And then minus f of x is minus x to the fifth, all divided by h. And now we're just going to use this thing that's been given to us, which is kind of a lot to write, but it's there. And we're going to replace x plus h to the fifth with all that. So we're going to rewrite this as the limit as h approaches 0 of kind of a long numerator, x to the fifth plus 5x to the fourth h plus 10x cubed h squared plus 10x squared h cubed plus 5x h to the fourth plus 1 h to the fifth minus x to the fifth, all divided by h. I'll point out that this expression here, this expansion of x plus h to the fifth, follows the usual pattern of the coefficients coming from Pascal's triangle, which I know I didn't write down, and the powers of x decreasing by 1 every time, and the powers of h increasing by 1 every time. That's always what I'm thinking about when I'm writing this out. And then finally, x to the fifth minus x to the fifth is 0. Those go away. Every remaining term has an h in it. So we can divide each term by h. So this is equal to the limit as h goes to 0 of 5x to the fourth h divided by h is just 5x to the fourth. 10x cubed h squared divided by h is going to be 10x cubed h. 10x squared h cubed divided by h is going to be 10x squared h squared. Every term, the power of h just decreases by 1. We get 5x h cubed, we get h to the fourth. And then every single term that has an h in it, well, if h goes to 0, all of those things are going to go to 0. You're going to have 10x cubed times 0. You're going to have 10x squared times 0 squared. You're going to have 5x times 0 cubed. You're going to have 0 to the fourth. And so what we're left with is just 5x to the fourth, which probably isn't surprising, but good to take note of. So we'll go one step further and actually do it for any power. Yeah.
Why did they all?
So we're taking the limit, right? So the step I kind of skipped was saying if we actually take the limit of all this, we're going to get 5x to the fourth plus 10x cubed times 0 plus 10x squared times 0 squared plus 5x times 0 cubed plus 0 to the fourth. And more generally, though, to answer that question, whenever we're taking a limit, if we can just plug in what, in this case, h is approaching and get an output, we're good to go. We couldn't do that in the very beginning, because in the very beginning, if we plugged in h equal to 0, we would have gotten x to the fifth minus x to the fifth over 0, which is 0 divided by 0, which we know means we have to do more work. So we did more work, and then we plugged in 0 at the opportune moment. So now we're going to do the same sort of thing, except we're going to do it for any power p. So we're going to find f prime of x for the function f of x equal to x to the pth power. And before we start doing this, I'm just going to point out that our f of x plus h, which is going to be x plus h raised to the pth power, if we went down and looked at the pth row of Pascal's triangle, I don't really know what the numbers are. It's that I know like 4 of them. I know that the first coefficient is going to be 1 times x to the p power. And I know my next term is going to be p times x to the 1 less power times h to the 1 more power. And then the next terms, I don't actually know what the numbers are. There's something times x to the p minus 2 times h squared. There's something times x to the p minus 3 times h cubed, all the way to the very last couple terms. Well, I do know the coefficients of the last couple terms because there's symmetry for this Pascal's triangle thing. So my second to last term, which I'm probably going to squeeze in here, is going to be p times x times h to the p minus 1, and the very last term is going to be 1 times h to the pth power. So I've got all these terms. I don't know what the coefficient here or all the middle ones are, and it's not going to matter. So that's why we're not too worried about it. So let me fix this here real quick. And let me make sure I pass around the attendance form before I forget about that. So now we're going to find the derivative. So we're going to find the derivative of x to the p, which you could write like this. It's going to be the limit as h equals to 0 of my f of x plus h, which is x plus h to the p power, minus x to the p power, all divided by h. And I think we've seen this enough times now to have an idea of what's going to happen. We're going to write out the big long thing. The first x to the p and the last minus x to the p are going to cancel out together. The rest of the terms are all going to have an h. We're going to divide out an h and then let the rest of the h's go to 0. So same process, it just looks a little bit funkier. So we're going to have the limit as h approaches 0. Let's see, we've got x to the p plus p times x to the p minus 1 times h plus something times x to the p minus 2 times h squared. I don't really care about the next term, but I'll write it anyway. Plus something times x to the p minus 3 times h cubed. Plus more terms all the way to the very last two terms. P times x times h to the p minus 1 plus h to the p minus x to the p, all divided by h. And the same thing that happened last time is going to happen here. Those two terms are going to cancel. They add to 0. Every other term has h to a power, either h to the first, h to the second, h to the third, all the way up to h to the p. And if we divide each of those by h, all of those powers of h are going to decrease by 1. So we're going to rewrite this as the limit, as h goes to 0, of p times x to the p minus 1 times, there aren't any h's because h divided by h is 1, and then something times x to the p minus 2 times h to the first is h squared divided by h is h to the first, plus something times x to the p minus 3 times h squared, plus all the way to the last couple terms, we're going to have p times x times h to the, well, we subtract 1 from the power, p minus 1 is p minus 2. And finally, the very last term, h to the p minus 1. And now we're in this position where we can plug in 0 for all of the h's. So we can rewrite this as p times x to the p minus 1 plus something times x to the p minus 2 times 0 plus something times x to the p minus 3 times 0 squared, which is still 0, plus p times x times 0 to the p minus 2 plus 0 to the p minus 1. All those things that are multiplied by 0, those become 0. And so we really are left with just p times x to the p minus 1. So it's true that the derivative of x to any power is equal to that power times x to the 1 less power. A couple notes. Note 1, technically, we've only proved this to be true for p being a positive integer, like 1, 2, 3, 4, 5, 6, 7, etc. Because this formula is only really true if p is a positive integer. That said, this power rule for derivatives or for differentiation is true for all values of p. So the power rule is true no matter what the power is. So for example, I don't love that. Okay. So for example, I could say f of x is x to the 7th power, and instead of doing it the long way, you all could tell me that the derivative is, well, write it down. My old power was 7, my coefficient now is 7, and my new power is 6. Now, I'm also introducing a couple of notation things here. One way of writing a derivative is saying the function is something, and the derivative, we read that as f prime of x. So I say here f of x equals x to the 7th, and the derivative f prime of x equals 7x to the 6th. Or we could say it this way. Let's say that I want to find the derivative of x to the negative 8th. So this notation here, this ddx notation means take the derivative of the thing after it. Well, I'll get there in a second. You're not wrong. I'll point out. Yeah. So this is going to be, let's see. So same rule, right? The power comes down in front, and our new power is 1 less. So positive numbers get smaller, negative numbers get more negative. Negative 8 minus 1 is negative 9. And yes, to address that notational question, another way we could write this would be to say our function y is equal to the cube root of x, or if you prefer, y is equal to x to the 1/3, and then you could say dy dx. But really, that's just shorthand notation for this. Check this out. This is really the derivative of y, which is the derivative of what y is equal to. So you could write this, it would look silly. You could write this as dx to the 1/3 over dx. You shouldn't write that. No one should ever write that. It's totally normal to write dy dx, be like, oh yeah, I'm finding the derivative of y with respect to x. But then when we're actually finding it, we replace y with the function that we're actually differentiating. Or you could just skip all this and say y prime. So again, the power rule is in play. We've got x to a power. The derivative is going to be 1/3 times x to the 1 less power. And 1/3 minus 1 is 1/3 minus 3/3, which is negative 2/3. I think there's one other thing I wanted to say here. So, what if, oh, I know what it was. What if our function was something like f of x equal to something gross like x to the 7 pi? I don't know what 7 pi is. I mean, it's somewhere, it's bigger than 21 because pi is bigger than 3. I don't care. All I'm going to do is throw the same rule at this thing. I still have x to some power. And so this is going to say that my derivative, which you could write as f prime of x, or if you preferred, you could write it as df dx. Well, same rule. The power comes down in front. And then that's going to be multiplied by x to the 1 less power. And so we literally just write in the numerator, in the exponent, 7 pi minus 1. That's all you can do. There's no further simplification that's possible. Then we can start asking things like find y prime for y equal to, sure, let's start that way. X cubed plus x times x to the 7th minus x to the 4th. Sure, that's fine. X to the 4th? Yeah, sure, why not? So, you may have heard of the product rule, but we're not going to use that here because we don't need to. And I would say a really good rule of thumb is whenever you're finding a derivative of something, it is often a good idea to simplify that something before you take its derivative. So here, if we just multiply this out, we can rewrite it as y equals, let's see, x cubed times x to the 7th is x to the 10th. X cubed times negative x to the 4th is minus x to the 7th. X times x to the 7th is x to the 8th. And x times negative x to the 4th is minus x to the 5th. And now we can take the derivative, or y prime. Notice, by the way, in the step where I just simplified, I didn't write y prime. I still wrote y because I wasn't taking a derivative yet. I was just rewriting the function still the same as it was before. But now we're taking the derivative and we're going to get 10x to the 9th minus 7x to the 6th plus 8x to the 7th minus 5x to the 4th. Let's look at a few more examples. Examples. So let's say we want to find the derivative of f of x equal to x to the 12th plus the cube root of x squared plus 1 over x to the 5th plus 9. And again, kind of like the previous problem, it's a good idea to simplify or rewrite this so that each thing looks like x raised to a power. So I'm going to rewrite this as f of x equal to x to the 12th plus, let's see, the cube root of x squared, that's x squared to the 1/3 power, but then you can multiply those powers and say that's x to the 2/3. 1 divided by x to the 5th is the same as x to the negative 5th. And 9. Okay, so then for most of this, we can just use the power rule. We're going to get 12 times x to the 1 less plus 2/3 times x to the 2/3 minus 1 is 2/3 minus 3/3, which is negative 1/3. And then instead of writing plus negative 5, we should just write minus 5 times x to the minus 5 minus 1 is negative 6. And finally, what's the derivative of 9? It is 0, because if you think about just the function 9 on its own, so if you think about, say, graphing y equal to 9, well, if you look at the graph of y equal to 9, it's just a horizontal line. And, oh, sorry, you can't see that. Apologies. And no matter where you look on that line, the slope of that line is what? 0. The derivative of a function is the slope of the tangent line of that function. But if the function is a straight line itself, the tangent line is always the line. And since this straight line always has a slope of 0, this function has a derivative that's always 0. So the derivative of 9, or any constant on its own, is 0. So we normally wouldn't write that, but I want to write that. Just to make that even maybe more definitive in your mind, if our function is f of x equal to 9, then we can take the derivative using the limit definition. So we can say, great, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay. This one might feel kind of tricky, but it's not as bad as it seems. If I plug in x plus h, what do I get out? It's not a trick. It's definitely 9. If my function is 9, no matter what my input is, it doesn't matter if I'm inputting x or x plus h or pi or a billion or negative a trillion, any input still gets me an output of 9. So I'm going to get 9 minus f of x, which is also 9, all divided by h. And this is where people, I feel like sometimes are like, James, it looks like you're going to get 0 over 0, but we're not. Because we're getting specifically 0 over not 0. That denominator isn't 0 until we actually take the limit. And so before we take the limit, we're going to say that 0 divided by not 0, like 0 divided by 3, is 0. And so we can say this is just the limit as h approaches 0 of 0, which is, you guessed it, 0. And that's the derivative of this constant, f of x equal to 9. It could have been any constant, right? It could have been 7 and still have been 7 minus 7 over h, or 13, it would be 13 minus 13 over h, or it could even be something weird like, for example, if your function is the sine of pi over 6. You may or may not know what that is, but here's what I definitely know for sure. It's not changing. Sine of pi over 6 is just some actual numerical value that is constant. There aren't any x's in there. If you don't see any variables, that thing is constant and its derivative is, everybody, 0. If it's sine of something, or if someone wrote something like, say, g of x was equal to the natural log of 17, I don't see any x's, so my derivative has to be 0 because my function was constant, even if it's funky looking. Okay. Let's do a few more examples because there's a few more things I want to say. Yes, just definitely that. So let's say we have something like f of x equal to 4x to the 7th plus 3x to the negative 5 plus 5x plus pi to the 6th power. I want everybody to try their best to take the derivative of that. All right, let's see what happens here. So for the first part, for this 4x to the 7th, the derivative should be, what's the number that should be in front here? One of my favorite numbers, actually. 4 times 7, 28. 28 is a pretty cool number. I'll tell you all about some other time. 28x to the 6th. And then for the next one, we're going to get negative 5 times 3, which is going to be negative 15x to the negative 6. What's the derivative of 5x? Just 5, right? When you see that 5x, you can think, oh, it's like a line, like y equals 5x, and its slope is always 5. So its derivative is always 5. Or you could use the power rule. You could say, I have 5x to the first, and my derivative is 5 times 1 times x to the 0. And x to the 0, right? We don't really want to write that, but you could think of this as 5 times 1 times x to the 0th power, which is just 5 times 1 times 1, which is just 5. Normally, we just think of it the first way, though, I would say. And of course, the derivative of pi to the 6th power is 0, not 6 times pi to the 5th, right? That's a constant. Its derivative is 0. So I want to point out, you all just used two rules that we haven't even talked about, and you did it kind of without even thinking about it. But the two rules we're using here are the following. If you're adding up a bunch of things and taking its derivative, you just take the derivative of each part separately and then add up the results. More formally, that's the sum rule for derivatives. The sum rule just says that if you're taking the derivative of f of x plus g of x, it's equal to the derivative of f of x plus the derivative of g of x. So you just take each derivative and then you add it all together. And you can do it for 2 things or 4 things or however many things you have added together. Yeah. Yes, the derivative of pi to the 6th, well, pi to the 6th power is a constant. It's somewhere in the neighborhood of 800. But since, right, that's a constant. How do I know it's a constant? What am I looking for? Yeah. Right, do I see any variables there? I do not. Pi is not a variable. Pi is a number. It's 3.14, whatever. So since that's a constant, its derivative has to be 0. So yes, what I would say is if you see a term that doesn't have any variables, typically x, although technically you use other variables as well, its derivative should be 0. You can't really hide a variable. I'm trying to think about all the kinds of functions that you really can't. You kind of have to see that variable. So if you don't see it, it means it's constant. People can make it look really gross though, right? Like I could write something silly like the derivative of 2 to the power of sine of 5 cubed minus 7. Oh, sorry, you can't see this. I don't see any x's. That thing's a constant. Its derivative is 0. So contrast that with the rule we were just using, which was the constant multiple rule, which says that if you have a function that's being multiplied by a constant and you take its derivative, I like to say that the constant just hangs out. So like when we took the derivative of 4x to the 7th, we did 4 times 7 times x to the 6th, but what we really did is we said, I'll just kind of give an example here. The derivative of 4x to the 7th really ended up being 4 times the derivative of x to the 7th, which was then 4 times 7x to the 6th, which ended up being 28x to the 6th. When I think about the constant multiple rule, the thing I think about actually is that I don't think about it. When we use this rule in practice, we kind of just do it without even realizing we're using it, which is great. That's kind of how it's meant to be. I will point out the more generalized version of the rule is if you take the derivative of some constant times your function, as I say, the constant multiple hangs out and you take the derivative of the function. One small thing I'll add in here is this sum rule. It's really the sum or difference rule. If you have functions added together, you add the derivatives together. If you have functions subtracted together, you subtract the derivatives together. So it's really the sum or difference rule. So I want you all to kind of make sure you remember this one because later on people start saying like they see something like a 5x and they're like, well, the derivative of 5 is 0, right? I'm like, no. I mean, yes, it is technically true, but the derivative of 5x is 5 times 1, which is 5. Or here, the 4x is 7. Right? The 4 doesn't go away. Its derivative isn't 0 because it's being multiplied by a function of x. So the constant multiple, as I like to say, just hangs out. All right, let's look at one more example and then we'll talk about some other things. What if I wanted to find for the function f of x equal to, where'd my example go here? Sorry. There we go. Yeah, sure. X to the 9th plus 2x to the 6th plus 7x cubed, all divided by x to the 5th power. Now I want to find the derivative. Well, again, there is a rule for doing something like this, and even though there is one, you shouldn't use that rule. You should, if you can, simplify first. And when you have a quotient like this, where there's only a single term in the denominator, it really makes a lot of sense to rewrite it as each thing divided by that denominator. So x to the 9th divided by x to the 5th, 2x to the 6th divided by x to the 5th, and 7x cubed divided by x to the 5th. And when you divide powers of a variable, you subtract the powers. That's going to end up being x to the 4th plus 2 times x to the 1st plus 7 times x to the 3 minus 5 is -2. So now we're ready to find the derivative because we've rewritten the function in a much, much simpler way. Our derivative is going to equal, let's see, the derivative of x to the 4th is 4x cubed. The derivative of 2x is just 2. And the derivative of 7 times x to the -2nd is 7 times -2, so -14. X to the -2 minus 1 is -3. So there's our derivative. I'll say it a lot. I'll keep saying it. It almost always makes a lot of sense to simplify your function before taking the derivative, if it's possible. Okay, let's do one of those. Cool. So a couple more examples here. This example is going to look at, so your variable doesn't always have to be x. In fact, it's not going to be, for examples we do, probably more in 17b and 17c. Like we're going to look at a lot of functions that have other kind of variables. Here's an example of one you'll see in the future. H of capital N is equal to, this is going to be a little bit annoying, r times n times 1 minus n over k. And I'm not just making this up. This is actually a function you will see later on. Okay, important question here. If I'm going to take the derivative, what's my variable? Is it r, is it n, or is it k? It's definitely n, right? Because I wrote h of n. This notation over here This is what's telling me that that's the variable. And everything else plays the role of a constant. So here we're thinking that R is a constant. It could be something like 2. And K is also a constant. It could be something like 3. So I'm still going to multiply this out. I'm going to distribute my R times N to each of those two terms. So I'm going to get R times N times 1 minus R times N over K. Or as I would probably prefer to write this, R times N minus, I'm going to write the R over K out front times N squared. So again, as far as this function is concerned, this R is a constant multiple, and this R over K is a constant multiple. So when we take the derivative, we're going to get R times the derivative of N to the first, which is just 1, minus R over K times the derivative of N squared, which is 2N to the first. And that's our derivative. It looks a little bit funky. You could write it like this. I probably would leave it like this, but you could also equivalently write it as R minus 2Rn over K. I will point out that a lot of the times when we're writing things with fractions, we like to go back and forth easily between writing a fraction multiplied by some stuff and writing that stuff multiplied by in the numerator of the fraction. They are the same, just written differently. Let's do, one more thing, we'll do that. So you definitely want to make sure the power rule gets embedded in your mind. It's going to be used a lot. And you're always just bringing that power down and subtracting 1 to get your new power. Your new power should always be 1 less than your old power. In fact, it's a good idea to remember that differentiation, if it's just x to a power, always lowers the power by 1. That becomes more important when you start talking about anti-differentiation in the second quarter of calculus. Okay, one more example before we switch gears here. Let's say we want to find the equation of the line tangent to f of x equal to the square root of x times x plus 6 at the point at x equal to 4. And what I would mention about finding equations of lines in general is to find the equation of a line, we always need 2 things. You need a slope and you need any point on the line. And so far we have half of a point. We have x equals 4, but we need to find the y value to get the ordered pair, the x comma y, to have the whole point. So first to find the point, we're going to say that, well, we know that x is supposed to be 4, and f of 4 is going to be the square root of 4 times 4 plus 6, which is 2 times 10, which is 20. So whatever our function looks like, it certainly goes through the point 4 comma 20. That point is on the curve. And then we also need to find the slope. This is calculus, and when they say find the slope of a tangent line, that means to us is that we're going to find the derivative of our function and then plug in the appropriate value to find the slope of the tangent line at that point. So to find the slope, we're first going to take the derivative. Before we take the derivative, we're going to simplify this to make it easier to deal with. So my function, which is the square root of x times x plus 6, I'm going to rewrite as x to the 1/2 times x plus 6, and then distribute that term to the things inside the parentheses. That's going to be x to the 1/2 times x to the first. Adding those powers, I get x to the 3/2, and then x to the 1/2 times 6 is just 6x to the 1/2. Now we're ready to take the derivative. So our derivative is going to be, again, power rules working here. So 3/2 times x to the 3/2 minus 1 is 1/2, plus 6 times 1/2 times x to the 1/2 minus 1 is negative 1/2. I would probably simplify this a tiny bit. I'd probably rewrite it as 3/2 x to the 1/2 plus 3x to the negative 1/2. There are other things you could do here as well. You could also write it as 3/2 times the square root of x plus 3 divided by the square root of x. Because x to the negative 1/2 comes down to the denominator is x to the positive 1/2, which then is the square root of x. And now that's the derivative as a function for any value of x, but we want to find specifically the slope at the point of interest. So we're going to plug in x equal to 4. So that we get that the derivative evaluated at x equal to 4 is going to be, that's kind of why I wrote it this way actually, so it'd be easier to see what we're going to get. We're going to get 3/2 times the square root of 4 plus 3 divided by the square root of 4, which is going to be, let's see, 3/2 times 2 plus 3 divided by 2. So that's going to be 6 over 2 plus 3 over 2, which is 9 over 2. I'll mention here, normally when I got to 3 over 2 times 2, I would have just written 3 because usually I like to write my things simpler. But I also saw that I had another fraction over here whose denominator was 2. So I was like, oh, it makes more sense to just say that 3 over 2 times 2 is 6 over 2 and keep the common denominator so that I can add those fractions together more easily. Okay, we're almost done. We found all the things. Now we need to put it all together in the equation of a line. Personal preference, I like the point slope form, meaning I like to start with y minus my y coordinate equal to my slope times x minus my x coordinates. That's the way I would always start. If we do it that way, we're going to get y minus, let's see, the y coordinate was 20 equal to my slope, which is 9/2 times x minus the x coordinate, which was 4. The only downside to doing it this way is oftentimes people want you to write it in the y equals mx plus b form. So then we could distribute the 9/2. Y minus 20 equals 9/2 x. And let's see, 9/2 times 4 is 36 over 2, which is 18. So minus 18. And then we add 20 to both sides to get y equal to 9 over 2 times x. And negative 18 plus 20 is plus 2. That's how I like to do it. But you could also have started off with y equals 9/2 x plus b and plugged in your x and y point to solve for b. We do it that way, plugging in y equal to 20 and x equal to 4. Then we can see that 20 is equal to, let's see, 9 times 4 is again 36, divided by 2 is again 18. Or you could just say 4 divided by 2 is 2, and then 9 times 2 is 18. That would also work just fine. And so this gives us 20 minus 18, which is 2, equal to b. The only downside about doing it this way is that once you found b, then you have to go back and plug b in to actually write out your final answer as y equals 9/2 x plus 2. But either way will get you to the same answer. I think I like doing it this way because you kind of just can start with it and just keep going until you get there. Whereas here you really have to kind of like turn around and plug back in. Either way is fine. All right, let's see, what do I got next? Oh yeah, this. Sure. So wouldn't it be wonderful if all of our functions were just x to some power? They're not. It wouldn't be one function. It'd be terrible because there's lots of other functions that we need to be able to deal with. So yeah, let's go that way for a moment. So before we start looking at other functions, I just want to point out a couple things. I know last class we briefly touched on differentiability. I just want to say a little bit more about it. So differentiability. Differentiability. Meaning, does the derivative exist? So if a function is differentiable at a particular point, its derivative exists there. If not differentiable, its derivative does not exist. So here's some examples of things that are not differentiable at a particular point. So something like this. If you have a hole in your function, you definitely can't find the slope of the tangent line at that hole because the function's not even defined there. There isn't a tangent line at that hole. Or if you have, say, like a vertical asymptote, also can't find the derivative at C. So both of these functions are not differentiable at x equal to C because the function doesn't even exist there. In fact, to be more specific, the function has to be continuous at a point to even have a chance of being differentiable. So let me actually show you one more example of not differentiable at C. Something like this, where you have some sort of jump discontinuity. This function also would not be differentiable at C. Even though it exists at C, it's kind of weird to think about like trying to draw a tangent line through that point there. Like there's like a lot of lines you could draw through that point that wouldn't really touch the function. So this is also not differentiable because the function's not continuous. Another way people say this is that differentiability implies continuity, meaning if you know a function has a derivative that exists somewhere, you know by default that it has to have been continuous there to even give a chance of being differentiable. That said, not every continuous function is differentiable. We've talked about a few examples before, like, let me just write, so note, each of these functions is discontinuous at x equal to C, which automatically means that they are not differentiable at C. But then there's plenty of continuous functions that are still not differentiable at specific points. Let me give you 3 examples. So f of x equal to the absolute value of x minus 2, which is just your usual absolute value function shifted 2 to the right. This function is for sure is not differentiable at x equal to 2. Yeah. Yes. And why isn't it differentiable at 2? Because the function isn't smooth. That's the way I really kind of think of it is. And actually, smoothness is a slippery slope because there are some smooth functions that still aren't differentiable. And we'll see one in a second here. But this one is not differentiable at x equals 2 because we have a pointy point, specifically a corner at 2, 0. Let me give you 2 more examples. And again, one of these we talked about last time, but I still want to show it to you again. So here's another example. Sure, we can make some room here. Another example is f of x equal to, x minus 1 to the 2/3 power, which looks like, I call this the bird function, because if you're ever a kid, you might have drawn birds like this, right? Well, this function kind of looks like that. It's been shifted 1 to the right, and it kind of looks like, let me do my best job of drawing this here. It kind of has that look to it. And it's definitely not differentiable at x equal to 1. Here we have what's called a cusp. Although again, I would just call it a pointy point. If you got a pointy point, not differentiable. I know it sounds a little silly, but like I remember pointy points. And finally, There is one other kind of way that your function can be continuous and still not differentiable, and it's kind of the weirdest way. The prototypical example for this is f of x equal to the cube root of x, or if you prefer, f of x equal to x to the 1/3 power. I'm gonna do my best to do this one. So when I draw, I'm always bad at drawing this one. So here we go. Let's use a different color. Yeah. Where'd you go? The color? Sure. So the thing I need to make sure I emphasize here is that when we get to the origin, the function gets very, very vertical for just a split second. Kind of looks like that. And this function is smooth. There's no pointy points. However, at the origin or somewhere, but in this one at the origin, I'll point out that f of x has a vertical tangent line at x equal to 0. What's the slope of a vertical line? Let's see. If I draw a vertical line, I've got a whole lot of rise over how much run? 0 run. The rise of a run is like a number divided by 0, which is undefined. So even though this function's smooth, the fact that it has a vertical tangent line means it is not differentiable at x equal to 0. So it is not differentiable at x equal to 0. You could also just see that by taking the derivative. And I think we did that last time too, but I'll just point out here that if you take the derivative of x to the 1/3, oh, we did this one. No, we did this one. Sorry. Yeah. We did this one this way. Our derivative is 1/3 x to the negative 2/3, which I would then really, really strongly recommend writing as 1 over 3 times x to the positive 2/3. And then you can see that if you plug in 0, f prime of 0 is 1 over 3 times 0, which is 1 over 0, which is undefined. So yeah, this function isn't differentiable at 0, because if you try to plug in 0 to the derivative, you get division by 0. And actually, the same thing is true for the previous one we did as well. If we look back for just a second here, this function here, if I tried to take the derivative, no, technically, we don't have the, sorry, we haven't talked about the chain rule yet, so I can't really differentiate that yet. So you just have to take my word for it. All right. So we've got so far derivatives of x to a power. There's lots of other types of, well, lots is probably, there's some other types of functions we would also like to be able to differentiate. And yeah, 2 examples I can think of. So what is the derivative of f of x equal to sine of x? Good question. So you could do this one way. I don't know if any of your teachers have, but one way to approach this is to use a limit definition. I don't really want to do that. Not because we couldn't, just because it doesn't feel like it shows us a whole lot. Instead, what I'd like to do is graph the function and then try to see if we can graph the derivative. So let's graph f of x equal to sine of x. We're trying to do a good job of graphing it here. So my period is 2 pi. I'm going to cut that up into 4 equal quarters. So cut it in half and then cut each of those in half. And then my amplitude is 1. So it goes up to a height of 1, down to a low of -1. And the sine function starts in the middle, right there. And then at pi over 2 goes up to 1. At pi goes back to 0. At 3 pi over 2 goes down to -1. And at 2 pi goes back to 0. That's one full cycle of the sine function. I feel like it looks a little blurry there. Okay. So trying to draw this as nicely as possible. It's always a sure way to make sure it turns out terrible. Say you can try to draw it nice. There's a pretty good 1 period of the sine function. And now we're going to try and graph the derivative by graphing the values of the slopes of the tangent lines. So I'm going to draw another XY coordinate system right down here. I'm going to line things up so they match. Okay, and I'll point, yeah, I should label this is pi over 2, pi, 3 pi over 2. Let's actually start with the easy ones. So at pi over 2, my point is pi over 2 comma 1. And if I were to draw a tangent line, the tangent line would for sure be horizontal. What's the slope of that line? Of that tangent line? This much, 0, right? Horizontal lines have a slope 0. So down here, if I'm graphing the derivative, the function value is going to be 0. And the same thing is true at what other value? Let's take over here at 3 pi over 2, the tangent line would also be 0, so the value would also be 0. Now, this next question is a little bit hard, but not impossible. If we look at the origin here, the tangent line looks like that. Certainly the slope is positive, and it looks like it's about 1, and it is 1. That slope of that tangent line there is a slope of 1. It's perfectly going over as much as it is going up. So at the origin, we're going to have a value, I should say, at x equals 0, our derivative is going to be positive 1. And then at x equals pi, it looks like we've totally turned around, and the slope of our tangent line is negative 1. Finally, at the end, we should be the same as at the beginning. If you've done a full cycle, you should have the same value you started with. So we should also have a slope of positive 1 over here. And then if we graph this, well, again, making it look nice, it looks like our derivative, what function does that look like?
Cosine.
It's cosine. And then you could even keep the process going. You could say, okay, well, except I didn't leave myself enough room on this piece of paper. You could then do the same thing to draw the derivative of cosine. So if I look at the slope of the tangent line here, it's 0. And then the slope of the tangent line here at pi over 2 is going to be negative 1. And then over at pi, it's going to be 0 again. At 3 pi over 2, it's going to be positive 1. And finally, at 2 pi, it's going to be 0 again. So now if I graph this one, it kind of looks like I took the sine function and flipped it over the x-axis, which is exactly what we have, which is negative sine of x. So our second derivative is equal to negative sine of x. And I'm not going to draw the next one, but if you took the derivative of sine and got cosine, then the derivative of negative sine should be negative cosine. So the third derivative here would be negative cosine of x. And if you take the next derivative, you'd be back where you started. Some notation here, the fourth derivative I'm going to write as, so after you get to the fourth derivative, you stop writing the little prime notations and you write the number in parentheses as a superscript. So the fourth derivative is f parentheses 4 of x would equal to sine of x, back to where you started. Another notation for this, if you prefer, would be d fourth of f dx to the fourth. That's another way of writing the fourth derivative using the Leibniz notation. It's kind of annoying, but it is what it is. So the derivatives of sine and cosine just go in a cycle. But specifically, what we really want to remember from this is that if f of x is equal to sine of x, then the derivative is equal to cosine of x. And if f of x is equal to cosine of x, the derivative is equal to negative sine of x. There are other trig functions which you'll take the derivatives of later on. For now, these are the two we need to know. There's also one other function that we want to throw in along with the rest of these, which is e to the x. We're going to graph this one as well. So here's a pretty decent approximation of the graph of e to the x. And here's what's interesting about this graph. So right here at the origin, and so I will say the thing about say you kind of have to believe me when I say them, right? I wouldn't lie to you about this, but there's not really a good like way of showing other than like busting out Desmos and actually showing all the slopes that I say they are. But I will tell you that the slope of the tangent line right there, oh, at the y-intercept, which is 0, 1, the slope of the tangent line right there is 1. And I'll just pick one other point here. Over here at 1, e, the slope of the tangent line there is e. Or more generally, for any point on the exponential curve, the slope of the tangent line is equal to the y value. Right over here, whatever my y value is, the slope of the tangent line is that value. Or phrased another way, f of x equal to e to the x is the only function that is its own derivative. Exactly. I should say, or a multiple of it. But so the derivative of e to the x is e to the x. It's kind of neat. Is the only type of function whose derivative is itself. The reason I say type is because you can multiply this function by any constant. For example, if my function was like 4 times e to the x, then the derivative would be, well, the constant multiple hangs out, and the derivative of e to the x is e to the x. The main reason I bring this up is so that we can talk about some of the rules now. Because if you only have powers of x derivative, or if you're only able to take derivatives of powers of x, you can't really do anything interesting with the product rule or the push rule. So let's talk about those two rules. So product rule. So let me point out what the product rule does not say. So let me say what it does say first. If you take the derivative of f of x times g of x, you don't get the derivatives multiplied together. So I will say it's not equal to f prime of x times g prime of x. Let me show you an example. If I took the derivative of x cubed times x to the fourth, which I know is kind of a silly way of writing it, because you could just simplify this, right? Normally I would say simplify this and say, well, x to the third times x to the fourth is x to the seventh. And what's the derivative of x to the seventh? It's 7x to the sixth. If you try to do this thing here, it's going to turn out wrong. Let me show you what I mean. If we were to say that this was equal to the derivative of x cubed times the derivative of x to the fourth, that would be 3x squared times 4x cubed, which would be 12x to the fifth. Those are not the same. So I want to be extra super duper clear. When you take the derivative of two functions multiplied together, you don't just take each of the derivatives and multiply them together. What we do instead, which is actually the product rule, is the following. The derivative of f times g is equal to the derivative of f times the original g plus the original f times the derivative of g. And what's kind of cool about the product rule is you can actually extend it to any number of things multiplied together. So this is the typical product rule, but you can also have a triple product rule, which is say if you have the derivative of f times g times h, it's equal to f prime times g times h plus f times g prime times h plus f times g times h prime. Or the way I think about this pattern in my head is if you're taking the derivative of three things, you're going to get three pieces, and each piece is going to have the derivative of one of the things and the not derivatives of the rest. So you get f prime times the other things, plus g prime times the other things, plus h prime times the other things. And that would work for any number of things multiplied together. If you took the derivative of f times g times h times j, how many pieces am I going to get added together? 4. And each of those is going to have one derivative and the rest not derivatives. So we're going to get the derivative of f times the other things plus the derivative of g times the other things plus the derivative of h times the other things plus the derivative of j times the other things. Always works that way. It's kind of nice. So what we're going to do with this is now take the derivatives of some products that we couldn't do otherwise. For example, if my function, sure, where'd you go? If my y function is say equal to x cubed times sine of x, there's no way to take the derivative other than using the product rule. So my derivative, my dy dx, is going to equal. So I would point out, you don't have to think of this, you don't have to do all this extra work. So I'm gonna not do the extra work first. I'm just gonna say, and here's what I really say in my head. It's the derivative of the first function times the not derivative of the other function, and then you switch, vice versa. You leave the first function alone, you multiply by the derivative of the second function, and the derivative sign is cosine. If it's helpful, you are welcome to write down, say, that's f, and that's g, and then, oh yeah, I need f prime times g plus f times g prime. That's the gist. So why don't you all try taking the derivative of sorry, I wrote this in a very weird way, of x to the 7th power times cosine of x. Yeah. Could someone pass the sign sheet back that way? Thank you, appreciate it. So you can also take extra steps here, right? Like I just took the derivative of f and got 3x squared there, and the derivative of g and got cosine x there. But if you like, you can actually write it first as x to the 7th times the derivative of cosine plus the derivative of x to the 7th times sine. So, sorry, times cosine, apologies. Right, but then I still have to write another line because I actually have to take those derivatives. So then if I simplify, I'm going to get x to the 7th times the derivative of cosine, which is negative sine of x, plus the derivative of x to the 7th, which is 7x to the 6th times cosine of x. One kind of point I want to make is if you're writing this, you need that outer parentheses. If you write this, that multiplication symbol is going to get lost in the sauce, and it's going to look like you wrote x to the 7th minus sine of x, and where it's supposed to be x to the 7th times negative sine of x. And what I would really actually recommend doing is putting the minus sign out in front of the whole expression. So I think the best answer to this question is to write it as negative x to the 7th times sine of x plus 7x to the 6 times cosine of x. I generally try to write my x's for my trig functions in parentheses. It is not required. I just think it's a good idea because it reminds you of the fact that you're taking sine of some variable or cosine of some variable, right? It's a function. It's got to have an input. That sine, you have to have sine of something.
I first, and then is that?
That's so I'm guessing you did it more like, so you said it was going to be, and right, which is what I've been writing before, but I did it backwards this time. So yes, let's take a look. Let's take a look. If we write it the other way, if we do f prime times g plus f times g prime, we're going to get, see, f prime is 7x to the 6th times cosine of x plus f, which is x to the 7th, times the derivative of g, which is negative sine of x. Yeah, that's still the same. So the thing that's nice about the product rule, which is not true about the quotient rule, is that it doesn't matter what order you write things in, because addition, the order doesn't matter, right? 2 plus 5 is the same as 5 plus 2. And multiplication, the order doesn't matter. 5 times 2 is the same as 2 times 5. So you could actually write this kind of any old way you wanted to. So I just want to finish writing this here. 7x to the 6th cosine of x minus x to the 7th times sine of x. So you can write it as g times f prime plus f times g prime, or g times f prime plus g prime times f, right? As long as you have, all you have to remember for the product rule is that each function has to have its derivative multiplied by all the other functions. So if I've got an f and a g, I have to have an f prime times regular g plus a g prime times regular f. And yeah, the order doesn't really matter. It's the derivative of one thing times the not derivative of the other things. The order does matter when we start talking about the quotient, which, yeah, we'll get to in a minute. So let's see, do I have any more interesting examples? Oh yeah, let's do a triple product. Let's say our function was r of x equal to, sure, e to the x times x cubed plus 5x squared times sine of x. So now I don't just have a product of two things, I have a product of three things. I have an f, a g, and an h. So my derivative, my r prime of x, is going to have three pieces. It's going to have the derivative of e to the x. And so let's just write it down smartly. The derivative of e to the x times the other two things left alone, plus the derivative of g, so the derivative of x cubed plus 5x squared, times the other two things left alone, so e to the x times sine of x. And thirdly, the derivative of the last thing, sine of x, times the other two pieces left alone, e to the x times x cubed plus 5x squared. So it's kind of nice to write it out this way just to organize our thoughts, but it definitely does require a lot more writing. Right? Because now I'm going to take a whole another step to write down the final answer. So it's certainly fine to skip this step and just say, okay, well, the derivative of e to the x is e to the x times those two pieces, x cubed plus 5x squared times sine of x, plus the derivative of x cubed plus 5x squared is 3x squared plus 10x times the other two pieces left alone, e to the x times sine of x, plus the derivative of sine of x, which is cosine of x, times the other two pieces left alone, which is e to the x times x cubed plus 5x squared. One thing I would just point out or caution you against, when you're writing out these kinds of things, you really don't want to use the typical times symbol for multiplication. I would use parentheses or a dot. Or sometimes both, as you can see here. Sometimes I like to use both. But that dot means multiplication. Or just writing two things next to each other means multiplication if you haven't indicated anything else.
But it's still okay if I need the fancy X for the other one.
For your like your actual X?
Yeah.
Yeah, totally. Oh yes, definitely. Yeah.
That's what I always do.
Yeah. I'm not good at drawing the fancy X, but yes, you're welcome to use whatever type, whatever font you like for your X's. So let's talk about the quotient rule. I will point out, in my opinion, the quotient rule looks very similar to the product rule. So here's the quotient rule. If you want to take the derivative of f divided by g, it's going to equal, now here the order definitely does matter. It's going to be the derivative of f times g minus f times the derivative of g, all divided by g squared. I'll point out here, just as a reminder, that the product rule looks very similar to the top of the quotient rule. If you're doing the derivative of f times g, it's the derivative of f times g plus f times the derivative of g. To be perfectly honest, though, when I look at this, I don't say this in my head. What I actually say in my head is I'm taking the derivative of some top thing divided by some bottom thing. Here's the quotient rule again. And the words I actually say in my head every time I do this are, okay, cool. It's the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Notice that I did this in a slightly different order than it's written up here. Here it's written as the derivative of the top times the bottom, and here I've said it out loud as the bottom times the derivative of the top. It's okay to change the order of multiplication, but we cannot change the order of subtraction. So you have to make sure that the first thing you write is always the bottom times the derivative of the top, or the derivative of the top times the bottom, subtracting then the other way of doing it, the top times the derivative of the bottom, or the f times g prime. So that's really what I actually say when I'm doing this. It's like, okay, bottom derivative of the top minus top derivative of the bottom. That said, if you can simplify something first, you still should. So even though we have the quotient rule now, that first problem we did way back when was still better to do not using the quotient rule. So I will say also, you definitely want to memorize these rules. They're going to come up often enough. You should practice them enough until you have them memorized. Do enough product rule questions, do enough quotient rule questions so that you have learned the rule. So let's look at some examples. Let's say our function was e to the x divided by sine of x. Okay, so the derivative is going to be, here's how I'm actually going to write it. It's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Normally, I would skip the step of writing it this way and actually have just written e to the x there and cosine of x there. So let's do that now. So our derivative is actually going to be sine of x times the derivative of e to the x is e to the x minus e to the x times the derivative of sine of x is cosine of x divided by, you can either write it as sine of x parentheses squared, or you can use the abbreviated notation sine squared of x. So there's a couple more examples here. Say our function is f of x equal to x to the sixth divided by x to the fourth plus 3. Question, yeah. Yes, it is. And I think you might have missed when I talked about that, and we didn't really do a whole lot to prove it, to be fair. We kind of looked at the graph and said, oh, this graph looks in such a way that all the slopes of the tangent lines are equal to the graph values, which means the derivatives are equal to the function values. But yes, it is something we might talk about a little bit more in depth next week to give you, if you really want kind of like a proof that the derivative of e to the x is e to the x, but it's not really where I want to spend a lot more time because I think it's not that helpful to see it, to be perfectly honest. Like, I don't mind showing it to you. I just don't know how much you're going to benefit from that. So here, when we take the derivative using the quotient rule, it's going to be the bottom, x to the fourth plus 3, times the derivative of the top, which is 6x to the fifth, minus the top, which is x to the sixth, times the derivative of the bottom, which is 4x cubed. It probably didn't need parentheses there, but that's all right. All divided by x to the fourth plus 3 squared. Now, a lot of the times on your next exam where you're taking derivatives, they will give you a question like this and say, do not simplify. And if the problem says that, then listen to it, right? Don't simplify. But if you did want to simplify this, it's not too terrible. I probably wouldn't normally simplify this though. I would probably leave it as is. But just to show you, we did simplify it. We distribute the 6x to the 5th and we get 6x to the 5th times x to the 4th is 6x to the 9th. 6x to the 5th times 3 is 18x to the 5th. And x to the 6th times 4x cubed is 4x to the 9th. All divided by, I would not multiply at the bottom, x to the 4th plus 3 squared. And then finally, I could subtract 6x to the 9th minus 4x to the 9th is 2x to the 9th. So this is going to be 2x to the 9th plus 18x to the 5th divided by x to the 4th plus 3 squared. But more times than not, you're not going to be asked to simplify these expressions. And if you're typing things into web work, you also don't need to simplify these expressions. Now, I will say, sometimes it's worth simplifying a bit so the thing you're typing into web work isn't terrible to type into web work. So that's kind of you have to gauge which is worse to do. Let's look at one more example here. What if our function was x to the 4th plus 3 divided by x to the 6th? Well, I could use the quotient rule, but it would be smarter of me to not. It'd be smarter of me to rewrite this as g of x equal to x to the 4th over x to the 6th plus 3 over x to the 6th, which is equal to x to the negative 2nd plus 3x to the negative 6th. And then the derivative is going to be negative 2x to the negative 3rd minus 18x to the negative 7th.